Assalamu alaikum, dear students. Welcome to Thin Film Technology lecture number 31. In this lecture, we will have discussions on the pulse laser depositions, that is shortly written as PLD, as a part of the lectures, common deposition methods for thin films and IC fabrications. I'm Dr. Pervaiz Ahmad. So let's start today's lecture with pulse laser depositions. So the sketch of the experimental setup is just like the one that you can see it here in this particular figure. So this is just like the falls that you can see it here. This is the falls. So here we have different part of the setup. That is, this is the motor. Here we have this is the targets. That is the fumes that we generated here, and here we put the substrate. I mean, here you can see the target, and then we have the substrate. So in between the substrate and the target, we generate the fumes. So here we place a vacuum gauge to measure the required vacuums, and then we have the power monitor. This is the power monitors, and the quartz. This is the quartz window, and the focusing lens. This is I mean, you can see it here is the focusing lens, and the beam splitter, and this is the beam splitter, and here we have the excimer laser, and this is a particular setup that's been separately shown. That is the beam splitter. I mean, there's you can see that what is this is basically the two targets. That is for the core deposition. I mean, we have two targets, and the two targets basically being utilized for the core depositions. So let's start the formal discussions. The characteristic of PLD. So what are the characteristics of the PLD? So by utilizing these techniques, we can reproduce the compositions of the target, and by utilizing this technique or by using these techniques, we have fast response, well-controlled deposition rates, and we remember this technique is environmentally Bayesian Bayesian technique, environmental Bayesian techniques. And we remember this technique is very flexible and easy to implement. Growth in any environment. I mean, this kind of the technique can do the growth in any environment, which is one of the very excellent characteristic of these techniques. Similarly, we can have atoms arrive in bunches. I mean, so there is no deficiency of the atoms, and we have bunches of atoms that arrive from the target to the substrates. So uneven, we have uneven coverage. So high defects are particulate concentrations. So this technique is basically not well suited for the large scale film growth. So fume generated by laser ablations with different tiny or microparticles. So here you can see in this particular graph, this particular micro graph, here you can see that we have a target, and this target, here we have the substrate, and when we shine the lasers, the laser beam on the target, so we generate a fume that is a plasma between the target and the substrate. So what happens? Falls are femtosecond to nanoseconds with a peak power, high NF. How much high NF? That is 100 of megawatt per centimeter squares. And what is the purpose of this? The purpose of this is to melt, then to boil, that lead to vaporizations, and at the end lead to ablate the target surface materials to atoms, ions, electrons, and clusters. I mean, these are been the overall process that has been summarized. That is what actually we do. I mean, in the overall process. That is, first of all, we have a pulse of femtosecond to nanoseconds with a peak powers, high NF to melt, and then boil, then to vaporize, and then apply the target surface materials to atoms, ions, electrons, and clusters. So here's we have the four-step depositions technique, the four-step that's been involved in laser materials interactions. That is step number one. That is in this particular step that's been designated as A. So what happened in this? Here you can see that this is the first step. In this technique, we have absorptions and heatings of the materials. Then we have the second process as been denoted as with B. So in these sections, we have meltings and flowing. And then the section number C, we have the vaporizations of the depositing material. And in section D, this is the section D. And in section D, we have plasma formation, just like you can see it here. This is almost corresponds to this process. This happening between the target and the substrate. So in D, we have plasma formation in front of the targets. So under certain conditions, the plasma can detach from the targets and propagate toward the laser beam. And this concept is being shown here. That is, we have certain conditions under which the plasma can detach from the targets and propagate toward the laser beam, that you can see it by yourself. So we have the pulse. For the pulse at the durations that we denoted by tau, if the duration is smaller than 10 picoseconds, so what will happen? The collision and the multi-photon, we will have collisions and multi-photon ionizations. What it mean? It means that plasma, we will have plasma formations without melting, and derivations, we will have deviation from tau under root tau scaling. This is the process, this is the conditions which we have when the pulse duration is smaller than 10 picoseconds. But if we have pulse durations and that pulse duration is greater than 50 picosecond, so we will have conventional melting, boiling, and fracture. So threshold fluence, that is joule per centimeter square for the ablation scale, as 10 raised to power 1 by 2. So this is how the fume generated by the laser abrasions with different 10-year microparticles. So what's the physics that's been involved in PLD? So let's discuss some parameters that's been relevant for the physics, and so that's we call the PLD physics. So we have what? We have metals absorption depth, that is approximately equal to 10 nanometers, and we remember it depends upon on the wavelength. Then we have relaxation energy. It is scale approximately. We have relaxation energy for a time duration of approximately 1 picoseconds. So where we have electrons, protons, and where we have electrons and phonon interactions. We have a relaxation energy that lasts for approximately 1 picoseconds, and where we have electrons phonon interactions. So incredibly non-equilibriums. At peak of laser pulse, temperature on the target can reach as high as greater than 10 raised to the power 5 Kelvin, with the energy greater than 40 electron volt. Electric field is greater than 10 raised to the power 5 volt per centimeters. Also high magnetic fields. So plasma temperature can reach from 3000 to 5000 kelvins. Ablated species with energy 1 to 100 electrons volt. So if we have a femto laser, so we remember we can do the polling with a femtosecond laser. That is, the photon density is so high, it focuses that a single electron can absorb several photons. The observed photons allow electrons to reach the ionization energy levels. The ejected electrons hit other atoms and amplify ionizations. These are basically the function of the femto laser, where if we utilize that in the PLD process. So all the energy is evacuated with the electrons, and a cold plasma remains at the machine's spot. The cold plasma expands from the samples. So all this happened in a few femtoseconds. That was mean by a femtosecond, that is almost 1 trillion part of a second. So in this duration, all these things happens in a femtosecond, that is 1 trillion time of a seconds. So there is no time for the heat to propagate over more than a few nanometers. So it's also an excellent macro machining tool with clean cut profile. So this is the setup. I mean the experimental setup for fuzz laser deposition system. I mean that if you have ever I mean the chance to visit a well-equipped lab for thin film depositions, so you can see this kind of setup, and this kind of setup is basically for the fuzz laser depositions. So here you can see this yellow like this yellow like red box. And this is basically the excimer lasers. And here you can see this drum-like structure. This drum-like structures, this is basically the chamber. And this chamber we have a view window. These two, these are basically the views window. And here is another setup that look like almost the ore, but it's another structure, another systems for the fuzz laser depositions. So here you can see that this one, the top one, is almost seem a bit advanced than this one. So this is the first scan, and this is the second type of the laser of I mean the setup, the experimental setup for our fuzz laser depositions. So we can have ceramic film depositions by PLD. So the property of the ceramic films that we can deposit by PLD is summarized on the left hand side of this tabular form. In the middle, we have summarizes the applications of the each properties, and then we have the ceramic materials. There's beans groups on the right hand side of this tabular structures. You know that these materials are quite complex. We've taken this from already published book. Maybe I'm not able to pronounce the full names, the full name of these structures. That's why I will leave that for you. So I will just take the property that is we have the high temperature superconductivity, and the applications of this property. I mean we have the material. These are the materials, and these materials they have the high temperature. Their properties. I mean they can work as high temperature superconductors, and their applications exist in microwave filters and delay lines, digital electronics, and sensor. And then we have these ceramics. These ceramics, they are ferroelectric. I mean, they have the ferroelectricity, and they can be utilized, or they have the application in ramps, capacitors, non-volatile ramps, optoelectronics, microwave devices, etc. Then we have these ceramics. These ceramics, they are basically ferromagnetic in nature, and they can be utilized in circulators, phase shifter, magnetic recordings, and antennas. Then we have these materials, these ceramics, and these ceramics they have the property that is called electrochromatic effect. And these kind of ceramic, which are the most popular, and this is vanadium pentoxide, and they are being utilized in optical modulators, sunroofs, sensor protections. And then we have these kinds of the ceramics, and these ceramics have the properties that is they are electro-optical effect. They generate the electro-optical generate, so that can be utilized as a transparent conductor, solar energy, and photovoltaics, etc. And these kinds of, then you have we can have all these these ceramics, and these are the excellent properties. And here's I mean the particular application where we can utilize. So be remember all these ceramics, they can be deposited. I mean this is the almost a non-ending list of the ceramic materials that we can deposit will help of PLD, fuzz laser depositions, and they have these excellent properties for these excellent applications. That is, the application exists almost in every field of modern technology. So this basically, summarizes the excellent uses or the excellent utilization of PLD and the modern technology. So that's all we have for this lecture. Thanks for watching. See you next lecture with further details. Till then, bye bye.